Hello and welcome to the Conceptual Design Review for Purdue DRAGONfly, Purdue University's submission to the NASA Floating Dragon Challenge.
Following the feedback obtained in the PDR, we improved all the systems and concepts mentioned by the judges, paying close attention to the possible issues they indicated. We have improved aspects of our concept to significantly increase reliability, efficiency, and most importantly, public safety. This can be seen in our CDR package, including designing the deployment system for redundancy, performing a 10G stress analysis on the wing and deployment systems, and changing to an overlapping wing design.
The flight of our node begins by the retraction of solenoid actuators, allowing the node to slide off the deployment system rail. The node then enters its first stage of flight, where it quickly nosedives through the thin upper atmosphere and past high altitude winds. During this flight stage, the split control surfaces on the cruciform tail act to autonomously maintain the node's orientation, as well as act as air brakes to keep the node from reaching transonic speeds.
After passing a jet stream region, our node will deploy its wing. The wing deployment mechanism will consist of a linear actuator connected with a Y rod, extending both wing out in a parallel motion and securing it in place. Once the wing is deployed, the air brake position will be adjusted in order to maneuver the node into a level flight position. This will prepare the node for the cruise operation. During cruise, the node will autonomously navigate using waypoint planning method, where each waypoint is set at some interval of altitude all the way up until the highest point before the drop, while keeping the latitude and longitude constant. This will allow us to make sure that even if the node drifts away from the targeted region, it will eventually circle back to follow the waypoint set at each altitude interval as it descends down. Through this, we can ensure that the node will land safely and accurately within the targeted region and the payload will be successfully delivered.
For the guidance, navigation, and control part of our design, we will employ the use of Pixar 6C flight computer with autopilot firmware. This will allow a design to function autonomously to glide, loiter, descend, and deploy parachute as it approaches the desired target waypoint. For the mission-specific operations, such as during our nosedive and wing deployment operations, we will further develop the autopilot algorithm using MathLink protocols.
A model was constructed in SOLIDWORKS to conduct a structural analysis on the node in its deployed and folded configurations to ensure that it met the 10G shock load requirement. As seen here in the folded configuration, the most stress is in the T-beam. Although it displaces slightly, the node does not yield at all. In this image, the node can be seen in its deployed configuration. As expected, the most displacement occurs at the ends of each wing. However, it is still within an acceptable amount and does not yield.
Following the PDR, we created a physical model of our air brake system to test in the university wind tunnel, which we used to obtain accurate drag coefficients for our air brakes at an array of deflection angles. With the results from this test, we were able to more accurately optimize the trajectory of our aircraft. Additionally, to ensure the feasibility of our asymmetric wing concept, we modeled the interaction between the wing and the horizontal tail surfaces using CFD. Using these results, we optimized the height of our wings so as to negate unequal forces on our aircraft.